Hello! In part 2 of an Introduction to Analytics, we'll dive in a little deeper using an example of analytics in action. One of the easiest ways to learn about analytics is by solving a classification problem by using a decision tree. This is because the problem we're trying to solve is easily understood. What class does each case belong to? And we'll use a model that's visually understandable rather than one that's purely mathematical. In decision tree learning, we construct a tree from class-labeled training records. A decision tree is a flowchart-like structure where each internal node denotes a test on one attribute, each branch represents the outcome of the test, and each leaf holds a class label. Decision trees where the class values are real numbers are called regression trees. Tree models where the class label can take a finite set of values are called classification trees. We'll be discussing a binary classification tree. In analytics, computers apply statistical learning techniques to automatically find patterns in data, and these techniques can be used to make predictions. We're going to use a decision tree to find patterns in a file that contains trivial data about houses so that we can make a prediction about each home's location. The first 7 columns contain features about each house, and we'll use them as predictors to determine each home's class, which will indicate whether it's located in New York City or San Francisco. Our predictors indicate the number of bedrooms and bathrooms in each house, its purchase price, the year it was built, its square footage, price per square foot, and elevation in meters. So even though we don't have access to any location data, like latitude, longitude, state, or zip code, we can still create a model to predict each home's location based on these 7 predictive features. Our file contains about 500 records, and I split it into 2 separate files. One that we'll use to train a predictive model, and one that we'll use to test the model's accuracy. Our classification task is going to use a supervised model, so I needed to annotate each record with its actual class value, like this. We have a binary class that can contain either NY for New York City or SF for San Francisco. To construct a classifier, we'll feed an algorithm a set of data that has already been classified so that it can learn a model. Our goal is to use the first annotated file to train a model, and the second annotated file to test the model so that the model can later be used to make location predictions on files that have not been annotated. For example, after we've built an adequate model, we can feed it a new set of 500 records that don't contain class values, and the model will predict their 500 locations. Using the records in our training file, we can draw a line that represents each home's elevation. You can see that all of the New York houses are within 73 meters above sea level. Since San Francisco is relatively hilly, the elevation of homes may be a good way to distinguish the 2 cities. Based on elevation, you could argue that a house above 73 meters should be classified as one located in San Francisco. But what about all the houses at or below 73 meters? Adding another dimension allows for more distinction. For example, New York condos can be extremely expensive per square foot, So visualizing elevation and price per square foot in a scatter plot helps us distinguish between the lower elevation homes. The data suggests that among houses at or below 73 meters, those that cost more than $1,776 per square foot are in New York City. We can visualize elevation and price per square foot as boundaries of regions in our scatter plot. Houses plotted within the green region are in San Francisco, and those in the blue region are in New York. Identifying boundaries in data using math is the essence of statistical learning. For the houses in the lower left white region, we'll need additional information to predict their locations. Analytical tools like R and Weka allow us to draw a scatterplot matrix, which visualizes all of the two-dimensional plot combinations using our 7 predictor features. For example, the plot in the upper right corner is a smaller version of the elevation and price per square foot scatter plot that we just saw. The 6 scatter plots in the far right column plot price per square foot against each of the other 6 predictors. You can see that there are some patterns in the data, but the boundaries for delineating them are not obvious. Finding patterns in data is where machine learning comes in. Machine learning methods use statistical learning to identify boundaries. Let's revisit the 73-meter elevation boundary proposed previously to see how we can improve upon our intuition. By creating a histogram of the elevations in our training set, we can better see how frequently homes appear at each elevation interval. While the highest home in New York is at 73 meters, the majority of New York houses have far lower elevations. A decision tree uses if statements to define patterns in data. For example, if a home's elevation is above some number, then the home is probably in San Francisco. In machine learning, these if statements are called forks, and they split the data into 2 branches based on some value. The value between the branches is called a split point. Homes to the left of that point get categorized in one way, while those to the right are categorized in another. A split point is a decision tree's version of a boundary. Picking a split point has trade-offs. Our initial split at 73 meters incorrectly classifies some San Francisco homes as being in New York. Look at the large green slice in the left pie chart. Those are the San Francisco homes that are misclassified as being in New York. These are called false negatives. However, a split point meant to capture every San Francisco home will include many New York homes as well. These are called false positives. At the best split point, the results of each branch should be as homogeneous as possible. The word we use for this in analytics is pure. The purest possible node contains predictions for only one class, not a mix of both classes. But this is rarely possible after just the first split. There are several mathematical methods to calculate the best split point, and the decision tree algorithm that you choose will automatically do the calculations for you. The algorithm that I chose compares impurity before and after a split for every feature, and then chooses the feature with the largest information gain. As we see here, even the best split on a single feature does not fully separate the San Francisco homes from the New York homes. To add another split point after the first one, the algorithm repeats the process on the remaining subsets of data. This repetition is called recursion, and it's a concept that appears frequently while training models. One reason that computers are so good at applying statistical learning techniques is that they are able to do repetitive tasks very quickly and without complaint. These histograms show the distribution of each subset repeated for each variable. The best split will vary based on which branch of the tree you are looking at. The algorithm takes a top-down approach to splitting the data by looking for the feature that makes each subset the most pure. For lower elevation homes, price per square foot is the best feature for the next if statement. And for higher elevation homes, home price is the best feature for the next split. Now let's use our histograms and pie charts to show how an algorithm builds a decision tree. I'll build it manually here, but your algorithm will do it automatically for you. As discussed, our first split is performed using a 39-meter elevation value. Neither of the leaf nodes on this branch are pure, so we'll split both again. Additional forks will add new information that can increase our tree's predictive accuracy. For lower elevation homes, we split on price per square foot. And for higher elevation homes, we split on home price. None of these leaf nodes are pure, so we'll split all of them again. Now, 4 of our 8 nodes are one solid color, so they are pure, and we will not split those 4 again. By now, this recursive process might remind you of the old 20Q game that tried to guess what you were thinking of by asking 20 yes or no questions. This is because 20Q's learning algorithm works via a binary decision tree. Each test has just 2 outcomes, yes or no. If we continue the recursion until we have all pure nodes, we end up with a large, complex tree that contains 26 leaf nodes. We added branches until the tree's predictions are 100% accurate, because at the end of each branch, the houses are purely in New York or purely in San Francisco. Do you remember the game Plinko on The Price is Right, where a contestant would drop a disc onto a pegboard and it would eventually fall into one of the spaces at the bottom? Well, let's turn our decision tree into a Plinko board and drop each house record down through the tree to see if it ends up on the New York space or the San Francisco space. Each disc here contains the 7 predictor values for one house in our training set. Because we grew the tree until it was 100% accurate, this tree maps each training house perfectly to the city it is located in. For example, as this house came to each if statement, its predictor values sent it down this winding path, correctly classifying it as a San Francisco house. And this home's predictors had it follow this path down into the New York pile. The data for these houses is called our training set because it was used to train our model. Of course, what matters more is how the tree performs on previously unseen data. To test the tree's performance on new data, we need to apply it to houses that it has never seen before. Here, we are sending down data from the houses represented in our testing set. Ideally, the tree should perform similarly on both known and unknown data. So our current model is less than optimal. We are interested in patterns that generalize, meaning patterns that predict well for cases that we have not yet observed. Overfitting is the tendency of a data mining procedure to tailor models to the training data at the expense of generalization to previously unseen data. Our model has learned to treat every detail in the training set as important, even details that turned out to be less relevant. There are many decision tree algorithms, like these examples here. Their names are mostly acronyms, so IT people should love this. The algorithm that I use to generate the decision tree is the last one listed here, C4.5. C4.5 became very popular several years ago when the International Conference on Data Mining ranked it #1 in its list of the top 10 algorithms in data mining. When I first ran the algorithm, I instructed it to create an unpruned tree with all pure leaf nodes so that I could demonstrate the concept of overfitting. When I altered the algorithm's parameters to create a more generalized tree by using reduced air pruning, the new tree contained only 6 leaf nodes, but it performed better with our testing set than the 26-node tree did. In this generalized tree, 3 of the 7 predictor features were deemed not significant enough to be used. Number of bathrooms, purchase price, and square footage were not used for split points. Here I show how many test cases were classified correctly and incorrectly at each leaf node. For example, all 93 houses at elevations higher than 36 meters are located in San Francisco and were successfully classified as San Francisco-based homes. The test that produced the most incorrect classifications was based on the year that a house was built. So if you follow the path down to where there are 8 New York homes incorrectly classified, you can see that the model struggled most with low elevation, low-cost homes with at least 1 bedroom that were built after 1969. This makes good intuitive sense because we didn't really stop building houses in New York in the 1970s. But if our model's logic was represented by a complex equation instead of an easy-to-read decision tree, we would have had a harder time understanding our model's weakness. When evaluating new data, your predictive model will never be 100% accurate, but knowing its likely error rate and the likely reasons for erroneous predictions will help you determine the model's appropriate use. Let's conclude by referring back to my statement about how analytical techniques can automatically find patterns in data. I chose to use a decision tree to introduce predictive modeling because it's like a transparent box whose construction reveals the structure of the patterns that it finds. Because they can be understood by people, decision trees serve to explain what has been learned. In other words, they explain the basis for new predictions. There are many more techniques, and some are so complicated that they are like black boxes whose internal workings are not very understandable. All of the techniques can make good predictions, but the difference is whether or not the patterns that are mined are represented in terms of a structure that can be examined, reasoned about, and used to inform business decisions. Experience shows that understanding what a model is doing is at least as important as its accuracy, because we use analytics to gain knowledge, not just predictions.